Today we're talking about fossils, more specifically fossilization, or the process of how an organism becomes a fossil. First off, let's decide what a fossil is. The strict definition of a fossil is any evidence of past life, a footprint, a hair, the impression of a seashell, an actual seashell. All of these are considered fossils. What are the different types of fossils? Well, they might be petrified, that is, turned to stone, replaced, that is, harder elements and minerals have replaced the soft organic material. You might have a mold or a cast. That's where the shape of an animal or its hard parts is preserved. Carbonization, where you basically have an impression of an organic life form. Copal is amber to you and me. This was a big list of words, but don't worry, I will be spending a slide on each one. Let's start with petrification. Petrified. So right here, the word that's obscured here is a cavity. This is petrified wood. Petrified wood is very common. A lot of the samples I have, which I have found on trails, is the same age as the dinosaurs. And even though it looks like wood and it preserves the structure of the wood, the actual wood itself is long gone. Every cell in this organism, just like you, plants are made out of cells. Every cell, bit by bit, was replaced. It was turned to stone. So over time, we have a stone version of what used to be a live tree trunk. So fossils are actually usually preserved as stone. They're no longer bone. And when you go to a museum, you see a dinosaur skeleton, you might be thinking, hey, that's bone. But nope, it's solid rock, very heavy. Each cell replaced over time with rocks and minerals. This is a form of replacement. So the squishy organic carbon-based cells in your body over time get replaced with harder minerals. That's how they last so long. Right here, these two Allosaurus, and you can see hadrosaur skull right here, a duck-billed dinosaur skull. These look like bones, but each bone was replaced cell by cell with harder minerals, which is how the fossil didn't decompose. It was preserved through a geologic process. A mold is what you get if you bury something hard, like a seashell. Then it gets dissolved, but the shape of it is stuck in the mud. So here is a mold of a beautiful ammonite. This is a squid relative that lived during the time of the dinosaurs. It's related to the chambered nautilus, if you know what that is. Now, sometimes a mold gets filled with something hard. If you were to squish your hand into wet clay and make a handprint, and then fill that handprint with plaster, the plaster cast of your hand would be a type of fossil. It's when the hollow space of a mold is filled with minerals. Here are some natural casts of more ammonite, that squid relative I mentioned. Carbonization. This is when the actual organic matter, the stuff that usually decomposes, gets preserved. Here is a honeybee that was preserved. It was squished, so usually this soft body tissue would easily decompose, but in this case it was just as if you were to smash a book on a living butterfly. You would create a carbonization of that butterfly. If you've ever smashed flowers between the pages of a book to make beautiful flat flowers for decorative purposes, that is a carbonization too. Copal. Copal's a really neat way to preserve a fossil. Probably you've seen Jurassic Park, maybe many, many times. If you've seen the original Jurassic Park or read the book by Michael Crichton, you might remember the science behind extracting dinosaur DNA. What you needed was something preserved in amber, which is a fossilized tree sap. Now, what's cool about this is the fossilized tree sap preserves the whole animal. It doesn't have a chance to decompose. Nothing eats it. It's not exposed to the air. All of its tissue remains. And in Jurassic Park, they extracted the DNA of a dinosaur from a mosquito that had sucked on a dinosaur. That would be hard to create a whole park full of animals. You'd have to get lucky and find a lot of copal with bugs in it. But it turns out copal with bugs in it is not too rare. If you enjoy jewelry and you like amber, you probably noticed that many little pine needles, parts of bugs, little leaves get preserved in amber. And if you like this kind of jewelry, I recommend the website Etsy, where you can find great fossilized organisms in copal, but be careful, there's a lot of fake stuff out there. Trace fossils. This category is huge. Usually we don't find the actual dinosaur bone, even though that's awesome and it can happen. It's even happened to me. But usually the animal doesn't leave its whole body behind. It leaves a lot of other traces that it was there. You can think of these as clues. They are indirect evidence. Maybe it's a track site. Maybe it's a burrow. Maybe it's poop. Coprolites are a really popular gag gift between geologists. I have received many coprolites from friends, and I have given many. It never stops being funny. Gastrolith. Now this is kind of cool. I will wait to explain it until we get to that slide, but these are easy to find. Right here you can see a burrow. So maybe the organism that was digging in the mud before the mud hardened into solid sedimentary rock, maybe it was a worm that lived in the ocean and it dug a hole in the mud and then the hole was preserved as a cast. You can guess what this is. This is a coprolite. And believe it or not, there are paleontologists that specialize in coprolites. Now, why would you study fossilized dung? Well, it's a really great way to find out what that animal ate. Not only that, they have gotten so high-tech with this stuff that they can detect microscopic pollen grains in ancient poop. Why is this important? Well, pollen comes from plants, and plants tell you what the climate was. Just like today, you only get certain plants in certain climates. The amount of information we can get from these trace fossils is enormous. I mentioned gastrolith. Gastro, of course, refers to your stomach. I don't know if anybody listening to this ever had a chicken or has a pet chicken now. I had chickens when I was a kid. Chickens, I know we're city kids, so I'm just going to say the obvious. Chickens don't have teeth. No teeth in that chicken. She just has a beak. And if you have pet chickens, you have to give them access to little rocks. Sometimes we feed them oyster shells that have been broken up. And the reason that the chicken will eat little rocks is because instead of teeth, she collects little stones in her belly. And that way, when the chicken eats food, whatever the food is, it gets ground up in her stomach by the gastroliths. Well, who cares about chickens? Chickens are a relative of dinosaurs. Dinosaurs did not go extinct. They just got smaller and arguably more delicious. Just kidding. I hope I didn't offend my vegan listeners. But it's true. This Thanksgiving, when you see a big turkey on your table, or if your family doesn't eat turkey, you can imagine one. That turkey is a dinosaur. The non-avian dinosaurs went extinct. The bird ones are still around, except they're not 18 feet tall and terrifying anymore. And just like modern birds will eat little stones to grind up food, dinosaurs did the same thing. If you traveled to the Morrison Formation or visit South Dakota or Wyoming, there are places where dinosaurs roamed the ancient US, and these are all over the place. I've gone there as a student in geology and as a professor, and you can pick them up and have a nice souvenir. The stomach acid tends to weather the rock in a really easily identified way. So it's very easy to tell these from, say, a cobble that was rounded by moving water in a river. They look very, very different, and they're a neat type of trace fossil. Okay, here's a nice trace fossil. If you've ever been to Mann's Chinese Theater, it's a classic theater and architectural site on Hollywood Boulevard. You can see a lot of movie stars' handprints and footprints. These are trace fossils too. Let's think about hard fossils again for a moment. Oh, here's another dinosaur footprint right there. Doesn't that look like a chicken's foot? There's a bird foot right there. Okay, now let's talk about the fossils. How come some animals' bones get buried and replaced by hard minerals, and then we get to dig them up and put them in museums? And how come others just are lost to history? Well, let's think about how to become a fossil. Now, everybody in here listening to this has had the experience of seeing roadkill. Roadkill. You know, maybe a skunk got hit by a car. Poor little skunk, and now it's at the side of the road. All right. What happens to that skunk's body? Now, maybe it rains. If it rains, the skunk's body could get washed away and the bones separated from each other. Or maybe scavengers find it. In that case, ravens, for example, or coyotes could eat it and break it apart. All of these circumstances would remove the fossil. It would never become a fossil. And in fact, most things do not become fossils. This is what makes fossils so special. Most animals, after they die, are scavenged or exposed to the elements and distributed and subjected to the weather. They decompose, they become dust. However, if you get buried right away, let's say a whole bunch of dirt falls on your head, and you have hard parts like hard bones and hard teeth, you might become a fossil. Why are fossils important? Well, as you have already learned in the subject of geologic time, we use fossils like dates. If you buy a carton of milk, there's always a date on it, the use by, the sell by date. This is how we use fossils. They're like little milk cartons stuck in the layers of rock, and each one only lived for a certain amount of time. If you find, for example, a Tyrannosaurus rex fossil in a rock, it is a Cretaceous aged rock. Now, I know the movie Jurassic Park had T-Rexes running around. However, T-Rex did not live during the Jurassic. T-Rex lived during the Cretaceous period, but Cretaceous Park just didn't sound as cool. I totally support the artistic choice there. When we use fossils to tell time, we use this old principle called the principle of fossil succession. This was invented by the geologist William Smith, a very famous map maker that helped to, modernize geologic maps and gave us a shortcut to identifying the ages of rocks based on what fossils they contained. Now, some fossils are more useful than others. An index fossil is any fossil that is a really strong clue to how old your rock is. An index fossil has to be found all over the world. That makes it useful. That means a geologist from Scotland can tell you how old a rock in America is. Also, they have to have existed for a short range of geologic time. If you pick, for example, a shark fossil, that would not be useful. We still have sharks. I would not be able to tell the age of the rock by a fossil of an animal that lived a long time. That's it for today. I hope after watching this, your lab is easier for you to complete. Take care, everybody.